All right, here we go. Chapter 4. Hopefully, I'm not too loud. We are opening a chapter on probability. And in our first lesson here, we are calculating probabilities and interpreting the results of those probabilities. So, like, how do we use them? First, let's look at an example that we've already seen. This was a case from several years ago where somebody, a company, suggested they could determine the gender of your baby ahead of time. So one of the things scientists will do when they're analyzing something like this is they will set up kind of what their tolerance is. So in the first case, they would say something like, well, if we have a case of 75 girls and 25 boys resulting from 100 deaths, then this would be considered like highly unlikely, right? That chance is not a part of this. This wasn't a random result. Because as we look historically at births, our probabilities of this occurring is like very small. And so whatever method that was used to do this must be effective. Whereas if your method is, slightly above the average, in this case, why, it's nearly 20% of the time that this occurs. Therefore, this may have been chance. All right? And so, therefore, the results are probably not effective. All right, another example of probability in life, this happens to not only athletes but also to people at work, is drug testing, where here we have some 530 people being tested, and we have different results occurring. And so one of the questions is, what is the probability of being tested and your result being bad? Meaning, either you were on drugs and they didn't catch it, or you were not on drugs and they thought you were. Well, we can see in this problem here that we have like 25 people who were tested positive and were not using drug. And likewise, there were 5 people that were on drugs and escaped, so to speak. So we can see here that our probability of testing in the positive sense, that's bad, it's about 5%. The fact that you would get a false positive. And the probability of I shouldn't say exactly, because 25 out of some 530 is probably not exactly 5%, but somewhere in the neighborhood. False negative would be a roughly 1%. And those, we don't, like, I can't tell you if those are reasonable results or if this is like an odd result, but that's just a matter of life. So what is a probability? Let's start with the basics. It is any collection of outcomes from a procedure. And then a simple event is an outcome that cannot be broken up into smaller parts. And then if we collect all those simple events together, and list them all together, then this is called the sample space. So these are 3 terms that will be bantied about as they go through probabilities. Important to have them in your notebook. Event, a simple event, and then sample space. Later on, we'll be looking at a problem like this. Here we have the probability of a child. Again, looking at gender, the probability of one person, one child. It's either boy or girl. That's the sample space. Whereas if you're looking at 3 children, then you have a sample space of 8 with all the possible combinations. Notation, how do we write this out? First of all, notice we use a P, which stands for probability, and then A is the event. 0 would be the smallest and 1 would be the highest, though many people say that there's nothing that is truly 0% probability and there's no 100% certainty either. More often, things are somewhere between these two extremes, which would be that which is impossible, that it won't happen, or that thing which certainly looks like it will happen, being thought of as the 100% chance. Okay? So important that you recognize and use this type of notation there. Okay? There are 4, excuse me, there are 4 possible ways to interpret probabilities. There is the relative frequency, and I'll go through each of these: classical, subjective, and then a simulation approach to probability. All right, relative frequency. This is kind of like looking back at history. We look at the number of times that A occurs, the number of times that the procedure is done, and then we declare that that is the probability. And we can look back at car crashes this past year in the United States. I don't know what year they were reporting the stat from, but basically the possibility that your car was involved in a crash was about 5%. Okay? 1 out of 20 cars are involved in some sort of accident. Just a little text exchange between who knows. All right, classical approach to probability. Here we have the number of ways that A occurs, the number of different simple events, okay? And here it's required that all outcomes are equally likely. So if we think about like rolling a die, flipping a coin, pulling a card out of a deck of cards, that kind of thing, those kinds of things are relatively likely. When we think about car crashes, some cars are more prone to crashing than other cars for various reasons. Because it may be because of driver habit, that kind of thing, blah, blah, blah. So not everything is equal there. So we can look at the lottery, for example, as a way to view classical. And different lotteries use different systems. I think here in Powerball lottery in Minnesota, we have something like 69 ways times 69 ways times 69 ways, because each one you've got different numbers, so to speak, 1 through 69, and then the last one is a 29, 1 to 29 that you pick. And so obviously there's only one of those that's going to work, and so we'll look at that problem in more detail later on. Okay? Just make sure you don't lose the ticket. Subjective approach to probability. Here it's just an estimate. We use the knowledge that we currently have and we kind of just spitball it, as they say. An example of this is, what is the probability of getting stuck in an elevator? We can look at some sort of historical nature of this, but this is basically, shot in the dark. Finally, we can look at simulation as an approach to probability. And here we use big, massive computers to do this well. And oftentimes looking at instances of, will a nuclear weapon be effective deterrent to a war? Well, you have to know if the bomb's going to work, and like you shouldn't really be blowing up bombs to make sure that they work because of radiation, blah, 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 blah. So if you want to simulate that, then we have to use these computers. Rounding rules. If it's a simple ratio, reduce. All right. If it's a more complex ratio, then you can round it to the nearest 1,000th. Okay, change it into a decimal, just round it off. So a few examples here of the rounding rules. I forget what example this was, but you get a decimal like that. Well, you can round it off to 0.445. And 1/3 can be should be left as 1/3. It could be rounded to 0.3333. Just don't round it off to 0.3 because that would be a poor approximation. And 2/8 again should be written as 1/4 or 0.25. All right, law of large numbers. Kind of an important rule that is the more we do something, the closer we get to the true probability. So as n increases, that is, we do more procedures, then the approximate probability approaches the actual probability. Caution here, this law of large numbers kind of works in experimental, but it does not work with like gambling. Like if you have a bunch of losses in a row, it's not like your next turn is going to be a win. Or if you have a bunch of wins in a row, it's not like you're on a streak and the next one's going to be a win, right? And the other thing that we need to be careful of is that all events are not equally likely. So, for example, the probability of you passing a difficult final exam in college, right? It's not like a 50-50 proposition. It depends on a lot of different things. So we've got to be careful there when we use the law of large numbers. So here's an example. And this one here would be the frequency, relative frequency approach. So in a past year, we had 3 million skydivers and 21 of them resulted in deaths. So, bam, 21 divided by 3 million, I believe, is 0.000007. We don't want to round that off to 0.0. We could say that's really close to 0, but that would be a situation where rounding would be not an advisable thing to do. Health insurers get really nervous when you check off the fact that you do skydiving. A classical example of probability. So what is the probability of having 3 children with the same gender? All right. So again, we look at that sample space of girl, 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 all the way through boy, 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 and there's 8 equal outcomes. We're interested in 2 of them, the first and the last, because those are the ones that have all gender equal, same gender, I should say. And so it's 2 out of 8, therefore 1 out of 4. All right. Here's an example of a subjective. All right, so this is kind of the spitballing approach. I don't know if you've heard about the Drake equation. The Drake equation is nothing you have to have down. Notice it's not highlighted, but it involves like what is the how many possible planets out there have intelligent life on them. And we look at all these different variables and multiply them together. And they're all estimates. The first one is like star formation. The next one is what is the frequency or what is the fraction of stars that support planets. All right. Some of these ratios are known. And I would say this one and even NE is known. Like how many planets, how many suns have, a sun has how many planets that are in the Goldilocks zone. So we know that probability, right? Whereas when we get to the latter ones, any of these here, they are at best a spitball. Because, for example, how many of them support life? Well, we don't really know. So these others that are estimates are exactly that. These are subjective probability examples. Somebody has kind of updated the formula a little bit. There's a Seeger equation now, which actually doesn't look at necessarily intelligent life, but just looks at the possibility of life, meaning does a planet have Earth-like environment? Well, one of the signatures we look for is oxygen or methane. And these kinds of things we can use spectrometers to detect from a distance. And so I think an astronomer has come up with this new formula, and the result has been roughly 2. One of the added new thoughts is that we have to have a quiet sun. That is a sun that is not like letting off massive amounts of flares and whatnot that cause those planets, obviously, to become barren. All right, back to Earth. Compliment. What is a compliment? Well, when you say something like, have a good day, that's great. But that's not a probability comment. A probability compliment is everything but the event A. And we write it as A prime. So keep in mind that the probability of A and the probability of not A is 100%, which is just 1. So the probability of not dying from skydiving, it's pretty high. Yeah, but in terms of life and death scenarios, we don't really like that because if that were the normal probability of like dying from going to school, that kind of thing, school would not exist as it is, or they would change it somehow so that, I know it feels like you're dying at school, but anyways, moving on. Significant probabilities, okay? What is a significant probability? This one's tricky. It's significantly high if the probability is less than, sorry about that, if the probability of X or more is less than 0.005. This means that you are beyond the second standard deviation. And I'll show you an example. We already talked about that, but I'll show you an example of what this is. But make sure you get both of these in your notes. So this 5% is like a threshold for high and low. If the probability is greater than that, then we say, well, that was probably just chance that occurred. If the probability is less than that, then we have to say that that was not chance. Something must have occurred. You were beyond the second standard deviation. And the example that I'm going to take you back to is at the beginning of the book, where this gender study that was done. Whereas in our first case here, our probability was less than 0.05%, 0.05. Therefore, that was a reasonably effective method of determining gender. Whereas here, we had about a 20% chance, and that was not considered effective. So that was due to chance. All right. So again, think about this as like due to chance. Finally, we close with looking at some odds. What are the odds of something occurring? And the odds against are written out as the probability against something and divided by the probability for something. And it's the reciprocal when you look at 4. That is, the probability is 4 is above and the probability against is below. And payoff odds, I'll go through that as well. So we kind of look through some basic ideas of determining what are the odds. So our example is the roulette wheel. There are 38 slots on the wheel, in case you weren't aware of that. And in this case, I don't know if this is true for all, but the payout is 35-1, the payoff odds. Okay. So the question can be, what is the actual odds against landing on unlucky 13? Okay. Again, keyword odds against. So we look at the probability for is 1 out of 38. The probability against is 37. out of 38. Therefore, the odds against are 37 to 1. So, yes, it doesn't really matter what number you pick, the odds will be 37 to 1 against you. Now, what is the payoff for a $5 bet? Well, the payoff, they told us, the ratio is 35 to 1, so we set that up, with n is to 5. So obviously, n here is 200 and, 175. Meaning if you put a $5 bet and you win, you would get $175 back, right, using those particular odds. A payoff with no profit for the casino. Now this is really weird because in all casinos operate with profit. So this is never going to happen in real life. But what they're saying is that this here is kind of the payoff odds are built in favor of the insurance company, are built in favor of the casino, right? They are going to make a profit. And so 37 to 1 would be the odds if there is no profit. And in this case, if you put a $5 bet down, you should get $185. And so notice here is where the casino is making a $10 profit off of every player that plays. Okay? All right. And that would be with the law of large numbers, right? I mean, you could win the first 2 times, that kind of thing, or, but in the long run, the casino is going to win because it's going to stay there. All right, good luck in your homework. Hopefully that was helpful.